Hello, everyone. Thank you for being here today for my presentation. So today I would like to present to you my research, which is about developing an adaptive network model in order to analyze cybersecurity threats in organizations. So let's get started. We all know that cybersecurity is an essential component in the digital world. With the increasing reliance on technology, organizations across all sectors face a growing risk of cyber attacks. One very notable incident that happened a few years ago is the Capital One data breach in 2019. In this breach, a hacker exploited a misconfigured web application firewall, gaining unauthorized access to sensitive information, including personal data of over 100 million customers. Which leads us to our motivation behind this research. Financial institutions face diverse threats, including malware, phishing, and ransomware. These attacks target sensitive financial data and disrupt operations, leading to severe consequences. These consequences underscore the critical need for cybersecurity strategies to protect financial organizations from evolving threats. Now, let's talk about our objective. Our objective through this research is to understand cybersecurity threats by developing an adaptive network model that simulates a cybersecurity attack. By doing so, we can get insights into how such attacks occur and identify strategies to prevent them, ultimately enhancing our ability to safeguard sensitive information and maintain security. Now let's move on to our approach. We're going to make an adaptive network model that will integrate elements from the cyber kill chain. Now, if you're wondering what is the cyber kill chain, let me tell you. The cyber kill chain is a framework that outlines the stages of a cyber attack from initial reconnaissance to the final objective. If we look to the right, we can see the different stages of the cyber kill chain. As we can see, we have reconnaissance, delivery, installation, command and control. So these are the different steps that a cyber attack goes through. Well, by incorporating this framework, our model aims to simulate the behavior of both the attackers and the defenders, providing a deep understanding of how such cyber attacks unfold and how they can be mitigated as well. Now let's move on to our network picture. As you can see here, we have the picture of our network. We have our model shows the different stages for the cyber attack from both perspectives, the organizations and also the attacker. So if you look at the first state X1, we have the initial states, which basically represents the initial state for the organization. But if you look at the state X2, which is reconnaissance, it is the first state. It is basically the initial state of the attacker. And then we have different states until we get to success or fail of the attack, and then what happens after. Now let's focus our attention on the different states that are also included in cyber kill chain. And this will help us understand the behavior of how cyber attacks unfold. And yeah, because these are like the elements of cyber kill chain. So in order to run our simulation, we're going to use an adaptive network-oriented modeling environment that was developed by Yanter. And for the implementation, we are going to use conceptual rule matrices to define state influences, connection weights, processing speeds, combination functions, and function parameters. Now let's look at our simulation results. So this is our graph from simulation. As we can see, we have different attacks over time. So this graph basically shows different attacks over time, and each attack period of it is 40 seconds. Now I want you to focus on one period only, which is basically one attack only. We can see that the red curve surpasses the green curve, which basically means that the attack was successful, since the red curve represents success of the attack and the green one represents a failure of the attack. Now, of course, this is not what always happens in real life, where we have a lot of external factors that can influence our model. So this is why we introduce adaptive state in order to reflect dynamic behaviors and interactions between the states. So if we look at our new network model, we have two levels. The first level is the base level, which is basically the model that we previously shown, which is also the level that includes the elements from the cyber kill chain. And then we have the first verification level, which includes the dynamic states that model the connection weights between the states. Now, before we move on to the simulation results, I would like to explain to you very briefly how we're going to approach our results. So we're going to look at that from two different perspectives. The first one is when the attacker learns better than the organization. I would like to outline that both parties are still learning constantly, but in this first case, it is the attacker that is learning better than the organization. As we can see, we have three different curves. We have the red one, which is success of the attack, the green one, which is failure of the attack, and the blue one, which represents the learning of the attacker. As we can see, the learning of the attacker constantly goes up over time, which translates to which shows these successful attacks over time. As we can see in the first 100 seconds, the red curve goes above the green curve. But as the learning of the attacker goes up, we have at the period 120 when the green curve, which is the failure of the attack, goes above the red curve, which is success of the attack. But then as the time goes by and as the attacker's learning gets better, we can see that the repeated successful attacks over time, which leads us to our outcome, which is the data stolen, which was represented by the orange curve in this graph. And now let's move on to our second case, which is when the organization learns better than the attacker. Again, I would like to highlight that both parties are always learning, but the organization in this one is learning better than the attacker. The red curve is always the success of the attack, green one is the failure, and the orange one is the learning of the organization. Now I want you to focus your attention on these two curves only, which is the success and the failure of the attack. As you can see, there's a lot of alternation between the two. So we're going to divide this graph into three different parts. So as we can see, the first part, the red curve surpasses the green curve, which basically means that the attack was successful. But then if we look at the second part of the graph, we can see that there are two alternations. The green one, at first there are two failed attacks, but then two successful attacks. This is due to the learning of the organization that it gets better over time. But then if we look at the third part of our graph, we can see that towards the 7th or 8th attack, the green curve surpasses the red curve, and it keeps going like that over time, which basically translates to the failed attacks over time. Let's look at the key findings. These simulation results show that as the organization learning become more efficient and persistent, the success rate in defending against attacks increases, leading to failed cyber attacks. This translates to the importance of continuous learning and adaptation in cybersecurity strategies. And now let's move on to the last part of our presentation today, which is the what-if analysis and risk assessment. What-if analysis and risk assessment are fundamental methodologies for evaluating the potential outcomes of complex scenarios. What-if analysis involves a systematic examination of the effects of various if factors, which are basically critical factors that can significantly influence outcomes. By varying these factors across specified value ranges, low, high, medium, it is possible to simulate different attack vectors and assess the likelihood of their success or failure. The results of these simulations are known as what factors, which basically provide valuable insights into the possible success or failure of an attack. Now, in order to complement the what-if analysis, we have the risk assessment, which involves assigning probabilities to each combination of if factors, offering a quantitative understanding of the risks associated with each potential outcome. Now let's look at our different if factors and what factors. Starting with our if factors, our first one is speed of vulnerability detection. This factors refers to the time it takes for the security team to identify a vulnerability within the system. The second if factor, which is the threshold of exploitation, it is the critical threshold at which an identified vulnerability can be exploited by an attacker. Then we have the speed of learning, which refers to the rate at which the system or security team can learn and adapt to new threats. And for the what factors, we're going to look at the data theft at 3 different points in time. So basically, we're going to evaluate whether the data theft occurs at t equal 40 seconds, t equal 80 seconds, and t equal 320 seconds. By analyzing the specific if factors and what factors, we can assess the potential impact on data security and the effectiveness of the organization's response mechanism during a cybersecurity incident. And now let's look at our table. This table represents the structured analysis of the potential outcomes of the scenario presented in this research. Based on this table, the table calculates the combined probabilities for each scenario by multiplying the probabilities of the 3 if factors. So, for example, we have 0.4 times 0.6 times 0.3 equal 0.72. I would like to mention that these probabilities are assumptions that were made during the research. They're not based on any statistical values, but in real life, it would be better if they're based on actual information and the statistical values that are provided by organizations. Yeah, so these combined probabilities are then used to assess the likelihood of the data theft at different points in time. 40, 80, and 320 seconds. And let's look at the simulation results. First of all, I would like to mention that when doing our simulation, we focus mainly on the red curve, which is the data theft curve, but we mainly focus our attention if the red curve surpasses a critical threshold of 0.3. This threshold was defined as a very important point. So, was basically if the curve surpasses the 0.3 threshold, it means that it's a case of data theft. But if the curve did not surpass 0.3, which means there was no data theft. If you look at the first graph on the left, we can see that the curve never reaches the value of 0.3 at any time, at any given time, which means that there was no data theft that occurred. But then if we look at the second graph, we can see that at our first point in time, t equals 40 seconds, the curve does not surpass the 0.3 threshold. But then if we look at the time t equals 80 seconds and t equals 320 seconds, we can see that the curve goes above the 0.3 threshold, which basically means that it is classified as a data theft. The analysis of the simulation results reveals a significant insights regarding the relationship between the threshold of exploitation, which is our second if factor, and the likelihood of data theft, especially when the threshold of exploitation is set to a high value, which in our case was 0.8. The simulation consistently indicates that no data is stolen, as the outcome values never exceed the critical threshold of 0.3. This finding underscores the importance of maintaining a high threshold for exploitation within the network security protocols. By ensuring that vulnerabilities cannot be easily exploited, the risk of data breaches is significantly mitigated. This highlights the critical role of robust vulnerability management strategies in cybersecurity, emphasizing that enhancing the threshold of exploitation is a key defense mechanism against potential data breaches. Incorporating this strategy into the overall risk management framework can greatly reduce the likelihood of successful cyber attacks and strengthen the organization's security. And thank you for your attention, everyone.